Today we're going to talk about a piece of grinding work holding called a thin V block, and also how you can mill high precision surfaces with low deflection and high surface finish. It can be useful in a grinder for shapes like this where we need to grind the faces perpendicular. It's also useful in a mill for timing features on a round object. And you can also do intersecting side holes all in one setup. You mount it in the thin V block and do your first face, intersecting hole, and your opposing face all relatively easily. We're also going to look at some copper clamping pads that can go with this and make marring parts much less prone, and it spreads off the clamping forces as well. So we'll start by machining the part in the Haas. I'm just popping in 2 holes so the end mill doesn't have to plunge when it goes to cut the V pockets. Kind of skipping through a bit here. We do the bulk of the roughing with a 6mm end mill, and that removes the stock and does a quick perimeter trim. The socket head slots get roughed in with a 4mm high feed mill, and we do not finish them at this point. I didn't have a tool to finish them in the magazine, and I figured I could just do it post-heat treat. And then finally we chamfer it. Some guys do not like to chamfer until after everything's ground, but I find if you have chamfers on the part when you're grinding, it goes much quicker. You're not fighting small burrs during setups in your grind operations. So I filmed this vertically. I have to apologize, but I'm explaining how the compliant layer trick works. You could use newspaper or paper towel, and you set your parts on and wet it and allow it to soak in. And then when you turn on the magnet, the high points of the part sink into the soft layer, and the low points are supported. And as you can see, as it's kind of starting to grind, you can see it's high in the middle on these 2 parts. So in my experience, this compliant layer technique improves the flatness from starting value by about 90%. So these were roughly 2/1000 out of flat, and after their rough ground, they'll be probably 2/10 out of flat. If it's grossly out of flat, like 5 to 10 thou, it's not a very good process. You should really look at shimming or setting it on the 3 points. So when we get stuff off the grinder magnet, always use a pair of jawed pliers or pry it off somehow other than sliding it on the chuck. The paper underneath, you could just throw that away. And a note on squeegeeing, you always want to swipe away from the wheel, not towards it. If you go towards it, you can run your hand into the wheel or the squeegee blade, and if you're doing finishing work, that can pretty much ruin your dress, and it's very annoying. So the parts are now flipped over onto that freshly ground face, and we'll rough grind the backside, and you can see how it's hitting on the points on the outside. So when you're doing the compliant layer, you want to point the high outer corners down. So you want to frown, not a smiley face, when we're thinking about how the part is bowed. But if you're shimming or on 3 points, you want a smiley face, not a frown. There really ought to be a whole separate video on getting parts flat. Now it's doing a quick dress, and then it'll go back in and finish grind. And I say finish grind lightly because we're not really going for finish or size here. Just it's a lighter grinding parameter with a little less heat in it is all. If I'm doing serious grinding, I'll allow it to dwell for 5 minutes between roughing and finishing. So we've rough ground both sides, and now we're going to see how flat they are before we get them to a flatter state. So they're about 4/10 over, and we're roughly 1/10.5 to 2/10 out of flat, and it has a little belly in the center. You can see I push on it and how easily it deflects. At this point, any kind of magnetic work holding is just going to pull that flat. We're not going to be able to get away from that. So we have to go to low deflection work holding at this point, and that's going to be super glue. I've struggled with super glue in the past. Then a young man named Cyrus, who's working at Professional Instrument this summer, told me the trick is to put it on the side between the chamfer, and it'll wick into low areas and stick to the chuck, and had much better luck since that one recommendation. We'll get it onto the grinder, kiss it off flat, that 1/10 or 2, and flip it, and then we'll make it both flat and parallel. Before any of that happens, though, we need to demag it. You can see how there's enough magnetism to hold them together, and that means it can also deflect it and bow it down to the chuck, even with the chuck turned off. Such a pleasant machine. So the chuck has been wiped clean and lightly stoned, as have the parts, and now we're just sliding them on, and we'll apply a couple beads of the glue. And like I said, just right in the corner, between the corner and the chuck, and you get really good work holding that way. And we'll hit some accelerator on that just to speed things up. And I don't normally worry about Sharpie too much. You can almost see when you're finished grinding, but this is more for the video's sake. Interestingly, in the book Holes, Contours, and Surfaces by Moore, they warn against overusing marker on the premise that it can load your wheel. Now that's for jig grinding, which have much smaller wheels and fewer grains and tighter grits. But I always found that kind of interesting, that the ink of a Sharpie can be a problem. You can see just that little tiny belly in the center is starting to wipe off. We're taking 5 40 millionths passes for a total of 2/10. These ought to be pretty flat at this point. We'll use the pliers to pop the glue loose. A note on once you get the parts off, there's some glue residue on the chuck. I have a very sharp cornered 90-degree square piece of carbide, and it just kind of knocks the glue off, and then you can acetone and stone it. So here we are checking for flatness. And it looks like we have about 40 millionths from end to end with a tiny bit of a swell in the center. But that's going to be adequate for moving forward. We're going to stick it in the Hermanschmidt vise. We'll grind the top, tilt the entire vise, and grind the side here. Then we'll pop them out of the vise, put them on the magnet, and grind the opposite faces parallel. So one thing I'm concerned about are these thin webs here and then the counterbore slot. When the wheel goes across, it's going to create a swell in this thin area, which will buckle up into the wheel. When the part cools, it'll dip. To combat that, with the vise kicked on an angle, we get a much shorter pass. Instead of the entire almost 75 millimeter length, it's only about 12 or 15 millimeters. It drives up the cycle time considerably. Instead of a window like this, we have a much larger boundary box, but I'll take that time penalty in order to have a flatter edge, because we have to consider that we're going to be holding these in a mill occasionally, and we want just a really nice straight datum to use for location there. So here are the tools we'll be using to hard mill. We're starting out with a 2mm 4-flute finisher, and this is back tapered, and then we'll use this to semi-finish the V's. Then we'll use a 2mm 2-flute CBN end mill to finish the V's, and then a 1.5mm ball mill to cut chamfers, and then a 4mm finisher, and we'll use that to cut the screw counterbores. That doesn't really need to happen, but I thought it would look better, and then we finish with a 5mm thread mill, and that'll cut the fastener holes at the top and bottom. So before we get going, I'll give the spindle taper a little squeegee. Now we're touching off tools. The CBN end mill getting probed. This is the tool changer mechanism. It kind of hides between the two Z-axis rails. The spindle comes up to speed before touching it off, and you could set that value. I have it at 15 seconds right now, but that allows for any axial displacement to work itself out. This is our 1.5mm ball mill. It's checking length and cutter radius. There's a air blast port that you see at 6 o'clock, and that is blowing any residues off the tool as it's checking it. I was always concerned running cutting oil how reliably I would get tool probing done, but it's not been a problem. So we check alignment. Since I'm just running everything on the magnet, sometimes you can have an errant chip or something throwing your vise out of tram. So anytime I do something like this, I always just quickly check. Next we probe for X, Y, and Z. I should also note you should check how the part is sitting perpendicular to the XY plane. And so we get it probed in X, Y, and Z, and we're ready to start cutting. We'll start with the screw counterbores. They got cut, and now we're putting on the chamfers. I like to cut chamfers before finished features when I'm hard milling, because if you cut the chamfer after you cut like a finished pocket wall, it tends to throw a small burr that's very hard to remove, especially if you have like a high surface finish. You can almost damage the wall trying to get the burr off. So I just have always found it safer to cut the burr or cut the chamfer prior to any wall finishing. Now we're semi-finishing the wall, and you can normally feed these tools much quicker than I am, but I was a little concerned about feeding into that undercut in the middle of the V. That's a lot of tool pressure all at once. I thought, we'll just take it easy and let it work its way down. And also, I'm blending at one of the corner radii rather than the middle of the flat. It's a little less disruptive in terms of the look. You can hardly ever notice if you blend on a radii like that. Now we're doing the CBN wall finishing. So this is feeding down 20 microns per pass, which is about 8/10. And you'll notice I'm not actually going into that corner radius. CBN end mills are really peculiar about being overloaded. So I just stay out of it and keep the tool pressure down. And you end up with a really nice straight wall with a really good finish. So this is the kind of finish it pulls off right out of the gate. It looks pretty good. Now we'll do the M5 thread mill. I got started a little late on the record, but you don't actually need a start hole for these. And the reason I chose to thread mill after heat treat is we know that it went 2 thousandths out of flat during heat treat. So if I had put those threads in prior to heat treat, they would have been out of perpendicular to the now cut V face. Which would have been a little frustrating. I could see that causing issues if it were more than 2 thou bowed. And really, I have to set it up once, so why do the threads prior to heat treat if I could just do that same setup after heat treat? It doesn't really take any longer, doesn't cause me any trouble, it's quite easy. So after the thread gets cut, the 1.5 millimeter ball mill comes in and cuts a thread chamfer. So normally on fasteners and hardened material I'll do a thread relief, but I didn't see it necessary the way the screw was loaded on this. This is pretty light duty. You won't be wrenching on this fixture. So. All right, moment of truth. We have the V block bolted to a toolmaker's cube, which is pretty darn square, and then we checked it for how it's sitting, and now we're going to check a known straightness shaft in relation to it. So this is the point when I noticed how I'm out of little aluminum clamping pads, and all the ones I had are actually a little too big, so I decided to make some copper clamping pads for this system, and I just had the Haas whip those up real quick. And then I'll deburr them by hand. Copper's challenging to burr. It almost needs to burr like multiple angles. And that's the end of the project. So thank you for watching. I don't get to share a lot of the stuff I do this way, so this seemed like a good excuse to show off.